Introduction to exercise 16A on the normal distribution. We're going to introduce a standard normal distribution as well, which is something slightly different. But the standard normal distribution, we're going to introduce the family of normal distributions as transformations of the standard normal distribution. That will come out later, probably in exercise 16B. And we're going to investigate the effect that changing the values of the parameters defining the normal distribution has on the graph. And then we'll look at, again, reviewing our understanding of mean, median, variance, etc., but in the context of the normal distribution. This chapter is all about the normal distribution, and I'm going to say that quite frequently. So I think it's important that we define what the normal distribution is. So if you flick to page number 21, you'll see this page here, and it's something that you may have seen before, this graph here. What's distinct about this graph? What is distinct about this graph? Go for it. No negative y values, good. So that everything's above 0, x equals 0, as we determined with our previous probability density functions. But what else is unique about it? Yes.
It's symmetrical and the y-intercepts at 0.
Perfect. It's symmetrical in y values around the y equals so the x equals 0 axis. Is that what you're saying? Or the y axis? Good. Anything else? You'll notice this is something that we see before. I mean, it comes with, for example, like a bell-shaped curve or something that looks similar to when it comes to comparing data. So, for example, if you're comparing VC results, you should end up with a graph that looks like this. Or if you're comparing the heights of every person in the world, you should have a graph that looks like this. So, realistically speaking, we use this to try to replicate everyday life statistics. In real life, data sets tend to have a bell-shaped distribution, as I mentioned, this kind of shape. For example, measuring the spread of weight, height, or IQ all have the most frequent element in the middle, right? In other words, the average. The average typically is in the middle, my apologies, is in the middle. And we can see that to the right-hand side, the left-hand side, we have less than common values for those. So this kind of distribution where we have the middle, where the median equals the mean, which also equals the mode, is what we call a normal distribution. All right, we can see that the very tip of it is both the mode, which is the most common value, the median, and the mean as well. This specific normal distribution, as you guys mentioned, it rotates it's reflected across the y-axis. This specific one's called the standard normal distribution. It's not to say that this is the only normal distribution, but this is the standard one. And we call it standard because it's followed by a specific formula, this one here. We use that specific formula, or the equation, sorry, to graph the standard normal distribution. You can still have normal distributions in other circumstances. For example, the average IQ isn't going to be 0, so the graph starts at 0. Average IQ would be about 100. And so the graph would have a mean or median at 100 or a peak at 100. It's still a normal distribution, just not a standard normal distribution. And we'll later on look at how we can change either from the standard distribution the standard normal distribution to the normal distribution we're working with, or the other way around and go from the normal distribution that we've got, changing that into the standard, what transformations would be applicable there. So the other point that we need to look at for the normal distribution is that the mean is 0. Right? And we know that because on our graph, we can see that the middle or the peak of that is at where x equals 0. And the other thing is that the standard deviation equals to 1. We've looked at how, for example, a certain 95% is between certain values of standard deviation. We're going to focus on that a little bit more. So each one of these dots or these segments on the x-axis represent one standard deviation. So this one here would be the average, or mu, as you guys are aware. This one here is mu plus 1 sigma, or 1 standard deviation. This one here would be mu minus 3 sigma, and you get the idea. So each segment shows 1 standard deviation difference. And that's going to come in very handy in later, because we're going to look at the idea of what those standard deviations mean. Okay. So and I know the wording's a little bit confusing, but run with me. If we are going from the standard normal distribution to a normal distribution that we've provided, I'm going to highlight the word standard to a normal. If we're focusing on those, this is the transformation we're applying, where xy coordinates are going towards sigma x plus mu, comma y over sigma. If we go the other way, and we go from a normal distribution, and it's missing that word, but it should say to standard, we do the opposite, and we end up with this formula here, where xy, or x goes towards x minus average over standard deviation, and y goes towards the standard deviation multiplied by y. Okay. Now, using this, you'll note that if we are trying to find the function of any normal distribution probability density function, we can substitute those transformations in and go from this general formula of our standard normal distribution to whatever values we're looking at. So we would substitute, for example, our average or our standard deviation, and we get a function that looks very similar to our normal distribution. It might be skinnier, it might be dilated, right? It might have been translated, but it's still a normal distribution. However, unless the average is 0 and the standard deviation is 1, it is not the standard normal distribution. I know it gets confusing because standard and normal are quite often interchangeably used in everyday life, but they do mean very different things here. Any questions? Okay. Last formula to look at before we move on. The conversion is useful in finding a value of a certain probability by using the probability of x being less than a, which you guys are already familiar with. We can say, if we use our normal distribution, where z is just a random variable on the standard normal distribution, so kind of like instead of x or capital X, we're using z, where z is less than or equal to a minus the average over the standard deviation. And again, it looks very similar because it's the same transformation that we've gotten from our transformation here. Any questions so far? Okay. Here we go. Let's move down to question or example 24. And this is an application of that transformation. So describe the sequence of transformations, hopefully you guys remember your stuff from chapter 3, which takes the graph of the probability density function of the standard normal distribution to the graph of the probability density function of the normal distribution. So we are going from standard to the normal. Okay. With the following mean and standard deviation, and sketch each distribution. So let's start with what formula we should be using. Well, the formula we should be using, because we're going from standard to the normal, if I flick back up over here, oops, there we go, should be the one at the very top where we have xy going towards sigma x plus mu, and then y minus sigma. So I'm going to write that formula just at the top right so that we know what that is. It's x comma y going towards sigma x plus mu comma y over sigma. There we go. Okay, so doing question 1, all we have to do is apply, substitute our values of mu and sigma in. So we know that xy goes towards 1x plus 3, comma y over 1, or in other words, x plus 3, comma y. In retrospect, I did not leave enough space for this question, but I'm sure you guys can fit it in. So it's pretty straightforward. The only transformation here is that we've shifted right 3 units. And it makes sense because remember the mu, or the mean, is the middle value, or the middle section of our normal distribution. And if the mean of this one is 3, whereas the one normally, or I should say use the word normally, in the standard distribution, standard normal distribution has an average of 0, it makes sense we just shifted the whole thing 3 times. And there's no dilation, so we're all good on that front. If I was to sketch that normal distribution, knowing that the middle is 3, and a standard deviation is 1, my apologies, and then going down 1 standard deviation gives me 2, and going up 1 standard deviation gives me 4. And then I can sketch that graph. You can do the same thing in your class pad, and we'll go through that in a moment, but I'm just going to open it up ready. So what we can do is we can apply those said transformations into the calculator in order to see what the actual graph would look like. We know what the normal distribution should look like. We have the general formula for it. We can substitute those values in order to find what that actual equation is. But before we do that, I want to jump to question 24C and see what happens when we have multiple changes in our variables. So again, I'm going to apply the same formula and define x comma y, going towards 2x minus 3 y over 2. So that's just applying the same formula from above, where we're substituting mu as negative 3 and sigma as 2. So we know if we were to write down an answer, we'd say a dilation of 2 along the x-axis. We'd say a dilation of a half along the y-axis. And we'd also say a translation of 3 units to the left, or in the negative direction of the x-axis. What I'm going to do is I'm going to go into my calculator, and I'm going to type in, and normally I like to type in more complex functions I'm going to graph into the main. And I do that because then I can see what that looks like before I copy and paste it over into the graph, because you guys already are aware the graph function only has a singular line of text. So I'm going to type in our normal standard normal distribution. So I'm going to type in, get my keyboard out, as a fraction, 1 over, and in this case I'm going to type in the general one, which is the one at the top, 1 over root 2 pi multiplied by e to the power of negative a half multiplied by e to the power of negative a half multiplied by x to the power of 2. I'm going to copy that and put it into my graphing table. Again, if you were to type this out here, it might come up a little bit odd. So I'd like to just type it out into the main function first. If you have it in the quick standard, it might come off a little bit weird. You're welcome to go into Zoom and Auto. It should give you a graph that looks like a normal distribution. And as long as you haven't done anything wrong, it should have a standard deviation of 1. So it shouldn't go too far to the right before it flattens out. And it should have a mean, or the median, or the middle value at 0. What I'm going to do now is apply our values into this new function here. So I'm going to copy and paste this one here. I'm going to type in, so in this case, the only differences are that there's a sigma here. Because if you substitute sigma y for y, and then divide both sides of sigma, you end up with that anyway. So in this case, our sigma was 2. So I'm going to type in 2 in the front here. And then I'm going to replace x. Here we go. I'm going to replace x with our new values. So x minus our average, which ends up being x plus 3. And then on the bottom we have 2. And if I sketch that, what's happened? Well, we've got a dilation of 2 along the y-axis. So we've stretched it out sideways. We've got a dilation of half along the y. Sorry, did I say x or y before? I meant x before. And then I've got a dilation of half along the y-axis, which means it's shorter. And then, of course, we've shifted it right 3 units as well. So that brings it from the standard normal distribution to our normal distribution. Any questions? Okay. As a quick reminder, I didn't mention earlier, but the formula for the maximum point on our normal distribution is always going to be 1 over our standard deviation multiplied by root 2 pi, which means that as our standard deviation gets larger, the steps in between, so our graph gets wider, doesn't it? Because as the standard deviation gets larger, those steps get larger, and therefore, those increments get larger, and therefore our graph gets dilated along the x-axis. But it also means, because of our graph, because of our formula for the maximum, that our y value, our maximum y value, goes down as well by a factor of that standard deviation. Great.